key conference. I will present Professor Siva. Professor Sivakumar Manickam is a chemical engineer specializing in process engineering of nanomaterials, especially in nanopharmaceuticals. Currently, he's working with the University Technology Brunei, and earlier he was with the University of Nottingham, Malaysia campus. His research group concentrates on the process development of cavitation-based reactors towards technologically important nanomaterials. His group is also looking into the development of pharmaceuticals nanoemulsions, extraction of natural products, as well as utilizing novel carbon nanomaterials to design biosensors for the early detection of cancer and diabetes. Earlier, he took various leadership roles: Associate Dean for Research and Knowledge Exchange, Director of the Center of Nanotechnology and Advanced Materials, and Head of Manufacturing and Industrial Processes. He was also the recipient of the JSPS Fellowship Japan. He has supervised about 50 PhD master students and published more or less 200 peer-reviewed journals and conference papers. He's also the Fellow of Royal Society of Chemistry, Fellow of Higher Education Academy in UK, and member of the Institute of Nanotechnology, ION. We welcome Dr. Sivakumar Manickam with his key conference, Petroleum and Chemical Engineering, University of Technology Brunei, Jalan, Tungku Link, Mukim, Gadong, Brunei. Thanks, Doctor.
Okay, so I can start, right?
Yes, you can start.
Yeah, okay. First of all, thank you very much. And in fact, I have to thank the organizers for the nice, maybe the invitation as well as organizing this conference. I'm very thankful to every one of maybe involved in this conference. Okay, thank you so much. And let me share my presentation now. So are you able to see the slide?
Yes, we can see the slide. Maybe you try to move to the second slide to confirm that it's not frozen. Okay, we can see the second slide.
Perfect. Yeah.
Okay.
Go ahead. Once again, very good morning, everyone. And I'm Siva. So I am with the University Technology Brunei. Earlier, I was working with the University of Nottingham for a very long period. Recently, I shifted to this new university just for a change. And my group actually working on this cavitation-based systems. And then we try to exploit this system for a variety of nanomaterials and nanoformulations. In fact, I started this technique in around 1997. So when I started my PhD, so I started using this technique. So almost 25 years we are working in this technique. And in fact, we are exploiting this technique to variety of materials and formulations, as I mentioned earlier. Not only we just work on the laboratory scale, we extend this to the industrial level. So we work intensively with various industries, biodiesel manufacturing, nanomaterials, nanoformulations, both in Asia and Europe. So these are the two areas we mainly concentrate. I hope through the presentation, you will understand what is this technique, what is the way probably we can exploit this technique in the nanomaterials and the nanoformulations. So actually where we are, I think you can see from the map. Just a minute. Yeah, so this is Brunei and is surrounded by Malaysia and very close to that Indonesia. And then you can see that Brunei is far away from Mexico. We are 15 hours ahead of Mexico. So here the time is Friday morning, 8 o'clock. So we are 15 hours. So I think this is the one, probably I think the longest time difference zone I'm attending. Okay. Anyway, I think it's good to meet the people over here. Okay. I think normally when we talk about the nanomaterials or nanotechnology in specific, we always talk about two routes by which we can obtain the materials. One is the top-down technique, which is nothing but destruction. I have the larger component, so try to reduce that larger component into smaller component. A good example, ball milling or grinding. Whereas the second strategy is bottom up or the construction technique, whereby we build the things by combining smaller components. In fact, we have a very good control in this strategy. That is the reason hundreds of techniques have been developed in this bottom up construction to obtain nanomaterials or nanoparticles. Sometimes we can think of coupling both these, top down and bottom up, so it becomes a hybrid technique. Now, when we talk about the nanomaterials or nanoparticles, especially on an industrial scale, commercial scale, what are the key things we try to focus? So, the desired objectives on a large scale. The thing is, whatever the technique or the synthetic method that you develop should be reproducible. Meaning that in the lab may be reproducible, but when we develop it to the commercial scale, sometimes it fails. So we cannot obtain the reproducibility, probably in terms of yield, probably in terms of purity. So definitely there may be some problems. So any technique when we develop, we should be easily able to translate to the commercial scale. That is a key thing. The next important thing, whatever the nanoparticles that we obtain should be highly monodispersed. So very uniform size and shape. That's very important. So the monodispersity again will decide the outcome of the materials in terms of properties. Because we are looking at the novel properties from the materials. So only with monodispersity you can achieve that. Normally, for the monodispersity, we are looking into the polydispersity index, maybe close to zero point 0.2, zero point 0.3, even at least to that level. And another important thing, the whatever that you obtain, the nanomaterial or nanoparticle, so definitely those should be free from surface defects. Because if you have surface defects, then you compromise on the properties. So we have to see to that they are free from surface defects. And lastly, no doubt on the commercial scale, all the industries they are looking into very easy technique. There is no complexity involved. Cheaper technique. So scalable technique. And of course, now we are talking about the sustainability and the environment friendly techniques. So these are some of the things even we have to look at it. So starting from reproducibility, monodispersity, free from surface defects, and other additional advantages. So we are looking into all this in our nano manufacturing technique that we develop. Classically, if you look at the energy source, because when we develop any technique, normally we try to employ energy to do the physical, chemical transformations. So, what are the classical or traditional energy sources that we employ? Very common heat, maybe light, or maybe even ionizing radiation. So, these are the very conventional energy sources we normally employ. But these days, we are moving towards greener chemistry, green chemical engineering. So there are various principles what it mainly targets. Always think about utilizing alternative feedstocks, alternative reagents, solvents, catalysts, and what is more important, always think about alternative energy stimulants. Meaning that as compared to the classical energy sources, think of alternative energy sources for your physical and chemical transformations. That is what the focus. Now, when we say that alternative energy sources, stimulants, are non-classical energy sources, good example, probably try to utilize maybe supercritical conditions that involve high pressure and high temperature conditions. Or you can think of utilizing microwave or maybe plasma. But this is what we are focusing. So the cavitation. So cavitation technique, what I'm going to explain to you is a non-classical energy source. We try to use it and then develop materials, nanomaterials or nano formulations. Again, there are various techniques under the cavitation. Very simplest one is using ultrasound. But on the commercial scale, we try to use hydrodynamic way. I will try to explain both these in detail so that you will get some good understanding. Okay. So my whole focus will be explaining these two techniques and then some examples. How do we utilize these techniques? So probably in your maybe materials preparation or formulations, you can think of utilizing at least in the near future. So what is this cavitation? So the whole focus is on cavitation. So what is this? Now cavitation is nothing but you have a liquid. In a liquid, you try to generate bubbles. So you try to form the bubbles, then grow these bubbles, and finally collapse these bubbles. So forming, growing, and finally collapsing the bubbles. This is what cavitation. So the cavitation involves three stages: formation, growth, and finally collapse. Remember, we induce the bubbles in the liquid, but once we induce the bubbles, the growth and collapse occurs automatically. Depending on the conditions we supply, definitely these will continue. So we form the bubbles, grow the bubbles, and finally collapse the bubbles. And look at the term. When the bubbles collapse, we say that implosive. They are not explosive. Now the difference between the explosive and the implosive, in the explosive, the energy is getting spread out, whereas in the implosive, the energy is getting concentrated. So in the cavitation process, we concentrate the energy in the liquid. That concentrated energy is very useful for your physical and chemical transformations. Now, what is the importance of implosive collapse? Or when the energy is concentrating, what it means? It leads to extraordinary extreme temperatures and pressure conditions. Even you can expect close to 5000 Kelvin and 1000 atmospheres at the local points of the liquid when the bubbles collapse intensively. Although these intense conditions are generated, remember they are occurring at local points. That's why we say that this cavitation is a local phenomenon. It is not a bulk phenomenon. You have a liquid which is a bulk, whereas at the local points of the liquid, you get this cavitation phenomenon. Although it occurs at local points, don't think that it is occurring at only one point or few points. It occurs at millions of locations in the liquid. Now, as a whole liquid, when it occurs at millions of locations, that is more than sufficient to drive your physical and chemical transformations. So you give enough residence time with the continuous generation of these cavitation points in the liquid, I think that will be more than sufficient for your physical and chemical transformations. So you can expect substantial physical and chemical effects through this cavitation phenomenon. So cavitation is very interesting, and we need a liquid in order to induce. Remember that. You cannot generate in solid or gas. You need a liquid system. Now, what are the four ways by which you can induce cavitation? The simplest way, just use ultrasound, ultrasonic waves. You heard of ultrasound? So use ultrasound waves in a liquid, which is nothing but acoustic cavitation or ultrasonic cavitation. That is what indirectly sonochemistry, probably you heard of that. So when we use the ultrasonic waves in a liquid, that will induce pressure variations because it's a wave. So it involves both compression and rarefaction waves. So definitely it will generate pressure variations that will induce bubbles in the liquid or cavities in the liquid. Similarly, on a commercial scale, this is what we are looking: hydrodynamic way of inducing cavitation. This is nothing but you take a liquid and using a pump, you just pass it through some specific geometry that will induce pressure variations. So using a liquid and using a pump, we generate pressure variations. Whereas using ultrasonic waves, we generate pressure variations. But on a large scale, this is very easy to do. But on a large scale, this is quite difficult. So for laboratory and pilot scale studies, we try to use ultrasonic waves. But for a large scale, we try to use this. So these two are laboratory and a commercial scale level very useful. But on the fundamental level, these two techniques are useful to induce cavitation. For example, optic wave. Nothing but you use a laser and then deposit high amount of energy in a liquid. That will induce cavitation. Similarly, we can use fundamental elementary particles like protons and then we can induce cavitation. But again, as I mentioned, for fundamental studies, we use this, but not for real commercial applications. When we want to develop any material or maybe formulations, then we don't use these two fundamental techniques. This is mainly for understanding. Anyway, we are not focusing on that, and we focus only on these two techniques. So at the bottom, you can see that ultrasound. Now, the ultrasound, definitely it involves frequency of the wave. Now the frequency is normally about 20 kilohertz, because below 20 kilohertz, you can hear the sound. Above 20 kilohertz, you cannot hear the sound. That is what ultrasound. Now, you pass the ultrasonic wave in a liquid. So it is a wave. So it moves in this way. So when the wave moves in this way, you have the compression and rarefaction cycle. Compression is nothing but high pressure cycle. Rarefaction is negative pressure cycle. So this is a positive, so it becomes compression. Because of increase in pressure, compression occurs. When it moves to the rarefaction side, then because of low pressure, so it is something like a vacuum, the bubble gets expanded. So when the wave moves in this way, initially you have the cavity. Now when it moves to the rarefaction, the bubble expands because of low pressure or vacuum. And then, so this is due to the rarefaction, and when the compression occurs, then it's compressed. So the bubble size becomes reduced. So when the wave moves in this way during the alternative cycle, the bubble compresses and expands, compresses and expands. In this way, bubble oscillates. Now, when the bubble oscillates, it can even suck the contents surrounding the bubble, which is nothing but the bulk liquid. So if you have some gases or starting reactant or any material in the surrounding liquid, when the bubble oscillates, these materials could be sucked, depending on the volatility. So the materials or the contents could increase, maybe just diffuse into the bubble, and then they can reach the interior of the bubble. But at one stage, the bubble reaches the maximum size, and then it cannot withstand. And because of the increase in surrounding pressure, then the bubble collapses. So it just bangs. When the bubble collapses, it leads to various conditions. Probably it can give the shock wave, it can give microjet, and it gives intense conditions at the center of the bubble. So finally, it leads to various conditions. Those conditions are very useful for our physical and chemical transformations. So in this way, the bubble oscillates and finally it collapses. With the collapse, we get extreme conditions, and those conditions are very useful. So at the bottom, you can see the sequence of the bubble collapses. So the bubble, and finally you see that the bubble collapse that creates the shock wave in the liquid. So we say that, okay, intense conditions are getting generated, but is there any experimental proof? Of course, Suslik from US, he did one experimental study in 1990. They published in Science, and that was the first experimental proof, clear proof that clearly shows that yes, intense conditions are generated. So what he did, he took the zinc metal particles in the liquid, and then at room temperature and ambient conditions, he put the ultrasound in the liquid. Now, as I mentioned earlier, when the bubbles collapse, they induce shock wave because the collapse is very intense, so it can induce shock wave in the liquid. Now, these shock waves more than sufficient to make particles to collide with each other. Now, if these particles collide with each other at a right angle, you can see that even they can melt. Remember, the whole liquid is at room temperature, but these ultrasonic waves, they induce shock waves. These shock waves make the particles to collide with each other. Now, at the point of impact, these particles then they start melting. Now, so effective melting occurs at the point of collision. Now, he back calculated using the volume of the melted region, then he calculated the amount of energy generated during the collision. And again, he calculated the velocity of the impact also. And what has been found out, it is half the speed of sound. And again, the effective temperature at the point of impact is about 3000 degrees centigrade. So finally, it has been proved that yes, intense conditions are generated. Now, when we talk about the cavitation again, so we generate the bubble. That is called nucleation. Grow the bubbles and finally make the bubbles to collapse. So the three stages. Again, remember, this cavitation you cannot generate in a pure liquid. A liquid without any impurity, a liquid without any gas, very pure liquid, you cannot generate cavitation. Because a pure liquid will have higher tensile strength without any impurity, without any gas, without any nuclei. The tensile strength will be very high. And ultrasound cannot overcome the tensile strength in order to induce the cavitation. So you require a very high negative pressure to induce cavitation, which is almost impossible. So a liquid with impurity or dissolved gases will generate easily the cavitation. Normally, in any liquid, we will have some type of gases or some type of impurities. So that will be sufficient to induce cavitation. Because in the presence of these impurities, the tensile strength of the liquid will be reduced. For example, you have some even small solid particles, very small sized particles, micron sized particles, or some dissolved gases, or maybe solids, some contaminants. They will act as nucleation centers to induce cavitation. So the tensile strength will be low. So when we use ultrasound, the negative pressure will be sufficient to overcome, and then it can induce the cavitation. Again, just for understanding, if you have pure water, probably you require 1000 atmosphere negative pressure to induce cavitation. Whereas when you use the tap water or normal water, even few atmosphere negative pressure more than sufficient to induce cavitation. So through this, you can understand that the cavitation or the cavity or the bubble, which acts as a mean to concentrate the diffused sound energy. Basically, it just concentrates the energy. That's why we say that it's an implosive collapse. In another way, each bubble generates finally intense conditions, so it creates hot spot. Alternatively, we can say that each bubble acting as a reactor, or we can say that it's a micro reactor. It's a very, very small one, so micro reactor. Now, think that you have water, just you are introducing ultrasound. Now, because of the intense conditions, the water even could be cleaved, and then finally it can generate hydrogen and hydroxyl radicals. Similarly, if you have the dissolved oxygen gas in water, it can break and then you can generate oxygen radicals. Now, once you generate these radicals, they can couple in different ways, and finally you start getting hydroxyl, hydroperoxide, water, and then hydrogen peroxide, hydroperoxyl, oxygen gas again. So you can get a variety of radicals and molecules. Simplest way, you can get variety of oxidizing, reducing radicals. So depending on the conditions, you can use these radicals and then you can try to do various reactions. This is the reason they people try to use the cavitation even for water treatment, because using these radicals, you can oxidize the contaminants, decompose the contaminants. So here you can see that the areas in which we can try to utilize this cavitation techniques. Not only in the nanomaterials, if you want to use it in emulsions, homogenization, and even the polymer dispersions, particle size reduction, generation of liposomes, capsulation, biotech processing, the variety of areas you can try to utilize this cavitation because of the conditions generated. So appropriately, you have to understand the cavitation process, and then you can use it for variety of purposes. So in the simplest way, we can say that it explores in maybe most of the areas of science and technology. Not only this has been utilized probably just for studies, even this concept has been used in making a Hollywood movie. Probably you heard of this movie in 1995, The Chain Reaction, the movie. The whole idea of this movie based on ultrasound. A Nobel laureate professor who discovers that using ultrasound, we can, and finally we can generate hydrogen and hydroxide. These hydrogen radicals could be utilized to generate hydrogen. We know that hydrogen is a clean fuel. So using ultrasound, why can't we generate clean fuel? That's the whole idea. But as you know that in any movie, and there'll be some bad days, they try to steal the discovery. So during that, he has been killed, but his postdoc, I think, then he probably fights, and then finally that's a movie. Anyway, you know the story. That's the way it goes. Now, what are the different factors which can impact the cavitation process? Because these factors have to be understood very clearly, then only we can utilize the cavitation process. When we use ultrasound, you know that the frequency is the key parameter. So you have to look at what is the frequency you are applying, because depending on high frequency, lower frequency, you get different effects. What is the intensity of the wave, amplitude? So depending on that, again, it can change the conditions. What is the type of solvent, especially what is the surface tension, what is the viscosity, what is the vapor pressure? We have to look at what is the characteristic of the solvent. That will impact the outcome. Even what about that type of gas dissolved? That will impact the thermal conductivity, heat capacity ratio. So we have to look at very carefully nucleation properties. So that will impact. What is the external pressure, whether it is at ambient pressure or you are increasing the pressure, and more importantly, the temperature. Because when you increase the temperature, you are reducing the you are increasing the vapor pressure, so it becomes easy for the cavities to form. But easy cavitation is one on one side, but these cavities could cushion the collapse of the cavities, which is not good. So temperature again has to be carefully utilized in the cavitation process. Normally we employ at room temperature only. That is very good in terms of economic point. Now I will show you like how these cavitation reactors, the simplest one. There are two ways we can use the cavitation reactors. One is the bath type, second one is the probe, rod, or horn type. The difference between these two, in the bath type, we use the transducer. This is what the heart of any ultrasonic system. The transducer is nothing but that converts one form of energy into another form. For example, this converts electrical energy into sound energy. Now, we attach these transducers at the bottom of the bath. Now you introduce your solution, reacting solution over here. Then you start sonicating the solution. So the ultrasonic waves will pass through the solution and then it will try to do the effects in the liquid. Now, this transducer is not in direct contact with the liquid. So it's an indirect way of introducing ultrasonic wave. But if you look at the second one, we put the probe directly into the liquid. So the probe is directly in contact with the liquid. There may be an issue, maybe after some time, contamination. Because same, the collapse of the cavities could erode the surface of the probe. By that way, metals could be introduced into the solution. So contamination may occur in the later stage. With the continuous usage of ultrasound, at one stage, it may happen. But now, since if you look at this system and then this system, here the surface area is large, here the surface area is low. That means the power introduced through a small area, so the intensity is very high. The power introduced through a large area, so the intensity is very low. So this is for high intensity applications, low intensity. So cleaning, for example, we use very commonly ultrasonic bath systems because cleaning requires low intensity. So definitely bath systems are useful. But for real materials development, formulations, and other purposes, we try to use these type of systems. I think again, here you can see different types of simplest systems. You must be seen in the lab, simple probe systems, high power probe systems, simple bath systems. Then these are different types of again standing wave ultrasonic reactor systems, and again some of the accessories used in the ultrasonic systems. These are the very common laboratory scale systems, but then slowly on the pilot scale and commercial scale. Here you see that multi-probe high power system, and you can see the flow path. So we can input the liquid, that liquid will experience the ultrasonic wave. Similarly, here you see the ultrasonic 1000-watt high power system. Now using a pump, you can put the liquid and expose to the ultrasonic wave. So slowly we can convert the lab scale into the pilot scale. And this is the one again we develop, which is a 15-liter reactor multi-frequency system. And using this, we can employ three different frequencies simultaneously, or probably one by one. We can do that, which is a high power system. And again, here you see that this is again industrial scale system. And here you can see that one module with, you can see the 5 rows and each one with 12 transducers. This is what supplying the ultrasound wave. So total in this single module, we have 60 transducers, which is a 37-liter capacity system. This is one module. Depending on the volume of the liquid, or maybe if you want to reduce the residence time, you can couple multi-modules. You can see that here, 5 modules. So 5 into 60, so 300 transducers in this module. By this way, one way you can expose to large liquids could be exposed, or probably if you use one module, maybe like 1 hour residence time required. But by using multi-module, we can reduce that time because you have multi-transducers. So in this way, slowly, we can try to go to the industrial scale, commercial scale, using ultrasonic systems. Now, what is the driving force? Now the question is, by using the ultrasonic or cavitation process, how this induces nanoparticles or nanomaterials. That is what the focus, again, the next focus. Now, when you induce bubbles in the liquid, immediately you can see that bubble and then surrounding liquid. Now, I classify into three regions. Core of the bubble, now the interface of the bubble. That means this interface with the liquid. So the core of the bubble, interface of the bubble, surrounding bulk liquid. There are three regions. No doubt, when the bubble collapses, the intense conditions will concentrate at the center. So you expect these intense conditions. But when you move out from the center of the bubble, of course, you cannot expect the same conditions. But at the interface, still the condition is close to 1900 to 2000 Kelvin. But the bulk liquid at ambient temperatures. Now, the bubble collapse occurs in less than a nanosecond. It doesn't exist for even 1 second. It occurs in less than a second. So, what you can expect, the generated hot conditions accompany very high cooling rates. That is the reason when you have a material, since the cooling rate is very high, the materials, they cannot organize in a very proper way, or they cannot crystallize. So it, this collapse hinders the organization and crystallization. That is the reason, if the material is able to enter into the bubble, normally we end up getting amorphous material. But of course, if your starting material doesn't able to enter into the bubble, it stays maybe in the interface, depending on the volatility. For example, you have a precursor or starting material, and that can easily enter into the bubble. Of course, then it experiences the intense conditions, and finally you will get amorphous material. But if the material has a low vapor pressure, cannot enter, probably moderate level, it can reach the interface. Still, the conditions are intense, it will result in amorphous material or sometimes crystallized material. But if the material stays in the liquid, you always get crystallized material. So, depending on the volatility or vapor pressure, definitely you will start getting maybe different nature of the material. Again, bubble collapse occurs very fastly. So the kinetics is very, very fast. So definitely it doesn't allow the growth of the nuclei. So that is the reason finally you end up getting smaller particles. So amorphous nature, this is the reason. And finally you get smaller particles because the fast kinetics due to bubble collapse, which occurs very fastly. Now, what are the inherent advantages we can get from the cavitation? Reaction rates are very rapid, but conditions are mild. You do it at ambient conditions, you can control the conditions, and you can avoid toxic reagent, complicated organometallic precursor. For example, you want to obtain material X. Conventionally, probably they may use complicated material, toxic reagent, but by using the cavitation process, you can change the raw material, reactant, feedstock, and you can obtain same end product. So it avoids the complicated organometallic precursor or toxic reagent. The interesting or very important point with the nanotechnology, we obtain smaller particles which are very uniform, and the size distribution is very, very narrow. And again, the obtained particles are very pure, and commercially, this is what industries are looking, highly energy efficient. That means using less energy, obtain the products. That's very, very important. Now I will go through some of the examples. I hope like you understood like what is the cavitation, how do we generate, and what are the different techniques and the fundamental understanding. Now, some examples, different materials from my group, what we have obtained in the last 15-20 years. That's what I'm going to show you. You know that in sunscreen application, they use the zinc oxide particles. Compared to using the larger size of the particles, if you use nano-sized particles, now you don't get the whitishness on the skin. If you use the conventional size, bulk size of the zinc oxide particles, you get the whitishness because larger size of the particles scatter the visible light. But when you use the smaller particles, it block. Actually, these particles they block the UV light, but since the size is very small, they don't scatter the light. So definitely they are very good. So how do we obtain the zinc oxide nanoparticles? We proposed a simple strategy, and here you see the size of the particles. These particles in the size range of 200 to 250 nanometers and very uniform sized particles. Once we developed this zinc oxide, that was our first nanoparticle synthesis, then we extended the same strategy to obtain a variety of nanoparticles. Actually, here is the strategy. We use an oil phase. You can take the waste oil phase, vegetable oil, or any other oil. You take the aqueous phase in which you put your precursor. For example, you look at here, I want to obtain zinc ferrite nanoparticles. So I take simple precursors, zinc acetate and iron acetate, put it into the aqueous phase, then use the ultrasound, induce cavitation. Now this aqueous phase has the starting material and it will be dispersed into the oil phase. After dispersing into that, these water droplets will stay in the oil phase. Remember, the viscosity of the oil phase is high, so the water droplets cannot move easily. They cannot agglomerate easily, coalesce with each other easily. Then you increase the temperature and then evaporate the water, and by that way, these droplets acting as a template, and then you get the smaller nanoparticles. So finally, we end up getting zinc ferrite nanoparticles. And then the next important thing is that in the carbon nanomaterials, one of the important nanomaterial, carbon nanotubes. But for many of the applications, the major problem with the carbon nanotubes, it's solubility. Normally, it doesn't dissolve in water, because if you try to dissolve it in water, it just agglomerates. It agglomerates into bundles. So we have to overcome the solubility issue. Of course, there are various ways by which people overcome this uh, issue. A simplest way, use a reflex method, and we have to employ a reflex for about 5 to 48 hours. So up to 2 days you have to do that. By this way, you carboxylate the carbon nanotube and then induce the solubility. But only thing, although it is inexpensive, but reaction time is longer. Sometimes the oxidation incomplete, and even we get aggregated carbon nanotubes. Then we propose the cavitation based technique. You take water and put acid, and finally you end up getting carboxylated carbon nanotubes, and the solubility is also very good. Now, even we quantified what is the number of carboxyl groups on the surface of carbon nanotubes, and you could see that, and you can easily see that we can, with an increase in time, the carboxylic groups on the surface of the carbon nanotubes increases. Now, what is very important again, with the cavitation or sonication, we can recover the carbon nanotubes even up close to 100%. But with the conventional method, the recovery is maximum 70%. Here you see the images. So finally, once we use cavitation with acid, the dispersion is very good. So the solubility is very good. So definitely, this is a very, very good method. Using this idea, then we extended this idea to other carbon nanomaterials like graphene, fullerene. In fact, we used, once we obtained this carboxylated carbon nanotubes and improve the solubility, we used this as a carrier for insulin molecules. And here you see that how do we do the insulin attachment. Of course, we publish papers so you can see the details. And finally, even we quantified how many number of maybe insulin molecules we can conjugate on this carboxylated carbon nanotube, which is about 0.24 milligrams for every 1 milligram of carbon nanotubes. Then we extended this idea to make nano dispersion of reduced graphene oxide. So here you could see that only by using the ultrasound, the dispersion is good and it is highly stable. And here you could see the images, scanning electron microscopy images of the obtained reduced graphene oxide. And again, we dispersed for different time period and at different conditions like pH. So we just checked how the stability of this. Again, we checked the size, zeta potential, and finally the scanning images. Once we obtain a good dispersion, then we used this dispersion for different applications, for example, in drug delivery as well as in the electrochemical sensing. I think just I will go through that, maybe just for understanding. Again, we use the cavitation and we try to exfoliate the graphite. You know that graphite is a multi-layer carbon layer. So we try to exfoliate so that we get single layer graphene or few layer graphene. And then we try to put the gold nanoparticles on the surface. So we obtain graphene gold nano composite. Again, after obtaining a good dispersion, we try to employ for electrochemical sensing as well as for cytotoxicity studies. This is another carbon nanomaterial, and these days people are trying to explain this fullerene, which is a buckyball carbon molecule. And again, we can use this to induce disperse in water. And again, conventionally, people are trying to use different techniques, probably using phase transfer catalysts or even other reagents. But we proposed a simple technique. And this is what the mechanism mainly, if you look at this, based on the cavitation, the bubble collapse, induce intense conditions, water is getting cleaved. So finally, you get the hydroxyl radicals. These hydroxyl radicals attach to the surface, and finally, you get the hydroxylated fullerene. So the simplest techniques by using the ultrasound, probably when you want to intensify, simply just put hydrogen peroxide and you get this product. We quantified even how many hydroxyl groups we attach at this stage, which is about 8 hydroxyl groups. And it's a very simple way, low cost techniques, and even we can produce on a large scale. And here, how do we do the separation, and finally how we did the elemental analysis and finally quantified. Here, the hydroxylated fullerene, slight is yellow color, and here is the size of the fullerene, hydroxylated fullerene that we obtained, DMSO. And again, AFM image, and probably like we just checked the solubility in different solvents. Now, this is about simple nanomaterial. Of course, hundreds of nanomaterials you can see in the literature, but just for understanding, I have shown based on the time limit. Similarly, nano formulations we can obtain very fastly. I will go through that. For example, nano emulsion we can obtain. Nano emulsion is nothing but you try to disperse one liquid into another liquid, maybe water into oil or oil into water. Depending on that, you get oil in water or water in oil emulsion. Now, once we disperse the droplet size, normally we try to obtain in the nano size range, which is 20 to 200 nanometer. So that is the way it becomes a very fine emulsion or ultra emulsion. Now, these nano emulsions are very useful in food industry, pharmaceutical industry, biotechnology, cosmeceutical industry. So very intensively exploited. Or you want to protect one component, encapsulate one component, you can use this technique easily. For example, in the pharmaceutical industry, it's very useful because using nano emulsion, you increase surface area, enhance the solubility, induce the dissolution, enhance the bioavailability. So you try to reduce the toxic effects overall. So because of these advantages, nano emulsions are very useful. Normally, to form the nano emulsion, you require 4 components. Definitely one oil, water. You require energy. This energy is nothing but cavitation. That's what we supply. And then to stabilize for longer period, we require a surfactant because that will reduce the surface tension of the dispersed droplets. Conventionally, there are a variety of ways we can obtain the nano emulsion or nano formulations, but we go for ultrasound. So this is what the mechanism. For example, I want to disperse oil into water. So by using the cavitation, it disperses and it forms the initial droplet. With the continuous usage, these droplets are further broken down. You get smaller droplets. So finally, it will stabilize. So how do we break the droplets? And finally, how do we prevent the droplets which can join with each other? These two are very important. That will decide the size of the final droplets we form. I think this is a very simplest way by which we can form the nano emulsion or nano formulations. Put one liquid, another liquid with the surfactant, and then you can use cavitation to form the nano emulsion. So initially, when we started this project, we utilized a very common drug, which is aspirin, a pain reliever. So we formed the nano emulsion of aspirin. And finally, you can see that when we use the normal stirring, how the droplets, when we use the even another ultra-thorax homogenization, how when we use the cavitation. So definitely it generates very, very fine droplets. And again, here you can see that when we use the conventional, creaming is the problem. With the ultrasound, there is no creaming. And again, the size is also very small and the polydispersity index also low. And so overall, when we use the conventional technique, you can form the emulsion, but it doesn't stay for a longer period. It phase separate. Whereas when we use the cavitation, of course, you finally form a very nice emulsion, very fine emulsion, which is stable for a very long period. In the industry, even they use a microfluidizer, which is a high pressure technique. Even they use 20,000, 30,000 psi to generate. In fact, many top companies, they use this microfluidization in order to form the nano emulsion or nano formulations. Now, we wanted to compare our cavitation technique with this microfluidization technique. This is one of the largest microfluidizer in the pharmaceutical industry. So we use our cavitation and compare with the microfluidizer how the size of the droplets that could be generated. What we found out, for similar levels of energy, ultrasound is 18 times more efficient, or the cavitation is 18 times more efficient with the conventional microfluidizer technique. You look at that, it generates very similar size of the droplets, but the energy is less energy by when we use the cavitation. Once we were successful, then we try to incorporate variety of pharmaceutical drug components, even natural compounds. Very common one, the curcumin, which is a very good anti-inflammatory, antioxidant compound, useful even in the cancer treatment. That's what people are claiming. This natural compound we finally encapsulated, so you can see a clear solution. And even this is one of the mushroom we extracted and then we encapsulated and formed the nano emulsion. Some of the products already in the market, and here where you can see that how the droplet size. Again, we extracted another active component which is beta D-glucan from this mushroom, and then we encapsulated in the nano emulsion form. Not only the normal emulsion, even the multiple emulsion we can generate using this cavitation technique. Not only we just check the size and maybe other parameters, even we preclinical studies, animal studies also we try to do and then check how the activity. And this is for the commercial system when we use a hydrodynamic cavitation. So you pump the liquid and then it passes through a geometry. By that way, induces pressure variations and then you can reduce the size of the droplets. So this is what the cavitation geometry present over here. It's called liquid vessel hydrodynamic cavitation reactor. We use this to generate again large scale nanoformulations, and even we can use for materials. This is curcumin encapsulated emulsion. And even in these days, we try to use the micro channel to develop these type of nano emulsions and the nano materials. And here you see that how the channel path. Here you can see the length of the channel and the diameter of the channel is very important. And finally, using this, we generate the emulsion. So diameter and the length of the channel is very important. Now, overall, I hope like I have given some ideas about the cavitation technique. How can we utilize it? Again, based on the time limit, I couldn't go very deeply, means many applications, but you can see in the literature, our reports, hundreds of papers we have already reported using this technique, and you can look into that. If any doubt, you can come back to me, no problems. Now the takeaway points. So definitely this is a very, very powerful and promising technique. You can utilize it for various technological applications. It is a very competitive technique and a superior one in terms of energy efficiency. It's a very simpler, cleaner and greener technique because polydispersity of the obtained products are less, stability is very good. And normally, if there is a necessity to use surfactant to improve the stability, we use a less amount of surfactant compared to the conventional products. Contamination we can reduce and the aseptic processing is feasible. These are some of my PhD students who did most of all this work. Of course, I didn't work actually in the lab. So all these studies supported by my previous postdoc and PhD students. I think they are working already in the industry or they are doing postdoc in Europe and the US at this stage. These are some of the agencies that supported all these research studies, government and industrial agencies. And these are some of my collaborators, and we collaborate for this cavitation-based research, mainly from Europe and Japan. And you have to understand that for the ultrasound cavitation, we have societies, mainly European Society, Japanese Society, and Asia Oceania Sonochemical Society. So there are three societies. We work together. We try to conduct conference almost every year. So this, I was chairing one of the conference in Malaysia a few years before, and there is a specific journal, ultrasonic sonochemistry, and it's a Q1 journal, and the impact factor is 7.5. So I am the executive editor. And if you do some related work, of course, you are free to submit to this journal. And even I've edited a book, and we are writing some of the review papers and books also related to cavitation. So you can get good idea by looking into that. And finally, here you can see my email ID. And again, Na- November 8, 9, and 10, we are jointly organizing a very big conference, and it's completely free, okay? Because it's a virtual conference. First time we are making it completely free. And if anybody wants to join, of course, you can just drop an email. I'm the coordinator for this conference. So I think I will make you to register and join this to explore intensively on this. It's a 3-day conference, and all the topmost scientists, they join and present their research work based on this cavitation and ultrasound based work. So please note down my email ID. Of course, you can see. And any doubt or any collaboration, any understanding if you need, please feel free to contact me, and I will be happy to assist you. Okay. I think with that, I think I'm on time almost. Thank you so much. And I will be happy to answer maybe if you have any questions. But again, feel free to contact me through the email ID. Okay. Thank you, NK. And now I will pass it to the maybe chair of this meeting. So, yeah, please.
Thank you, Professor Siva. So if there's any question, please, you're welcome to write them or on the chat box on the next side of the Google Meet platform, or you can raise your hand in order to open your microphone. And okay, Dr. Luis Villarreal, please go ahead.
Hi, Dr. Siva.
Yeah.
Thank you for the presentation. It's pretty interesting.
Yeah.
I have a sonicator device, and I have a ultrasonic bat in my lab. And but I use a technique for to prepare nanoparticles. I use the electrospray technique. Had you heard about it?
Yeah, I heard about it. Yeah.
I use that one, but sometimes when I try to put it in a solution, the nanoparticles created, I have good sizes between 100 nanometers, 200. But I have a problem with when I put it in a solution, and then I take it to the DLS, diffraction light scattering, to measure the size. I see high polydispersity. I think it's because it gets agglomerates.
Okay.
So what you can recommend me to put a sonication time, I don't know, before reading. But for application, what I should do?
Okay. I think two things you can look at it. One point is probably you can increase the intensity of the ultrasound. By that way, it can prevent the aggregation or agglomerate formation. But as I mentioned earlier, ultrasonic bath has a very low intensity. I just mentioned it. So probably it cannot prevent. Temporarily, it can just break the agglomerates so that maybe the particles may be like smaller size, but with the time they can agglomerate back. But if you use a high intensity ultrasound, it can permanently, it can make the particles not to agglomerate. So maybe you can try to use a probe system and then see like how the particles. The second thing, maybe if there is an allowance in your system, you can use a surfactant. You can use a smaller concentration of the surfactant and stabilize the particles. But normally we try to avoid using surfactant, but we use high intensity probes type of sonication systems. By that way, we can prevent agglomeration. In fact, without using surfactant, we have reported many papers in which we never use any surfactant. Even good dispersion you can obtain without using surfactant. So you can look at some other papers and feel free to contact me. Maybe like I can tell you also later on. Okay, no problems. Okay, I will tell you like, and slowly you can maybe avoid this problem.
All right, I will look for the papers. Thank you. Yeah. And I got the tips. Thank you for. Yes, we don't want to use surfactants, no, always.
Yeah, okay.
but it's great tips. I will check. I will check your papers. And thank you for the invitation for the conference. The that you participate in the editorial position that you have on the journal. Congratulations, and we look for it. Thank you very much.
Thank you, Dr. Villarreal. Is there any other question? ¿Hay alguna otra pregunta? Por favor, puede escribirla en la caja del chat en la parte derecha de Google Meet, o puede levantar su mano y abrir su micrófono. Puede ser en español y nosotros la traducimos en inglés. Okay, Lizette Perez asks, what is the percentage of loading of the drug into the emulsion? Did you already have made this test?
Yeah, correct. Again, it depends, okay? Depending on the drug molecule or size of the molecule, you can load. I think maybe you can look into our papers. We encapsulated different types of drugs, and depending on the drug, the encapsulation efficiency becomes different. For example, for curcumin, I don't have the exact value in my mind. Curcumin, it's a different thing. Aspirin, it's a different thing. Even the cancer drug like paclitaxel, it's a different thing. So depending on the drug, the encapsulation efficiency is different. But again, compared to the conventional emulsion, definitely we are encapsulating a high percentage of drug into the droplets. That you can look into our papers. So encapsulation efficiency is definitely very high in the case of like cavitation based technique. That's what we have reported.
Thank you, Professor Siva. Is there any other question? ¿Hay alguna otra pregunta? La pueden hacer en español, nosotros la traducimos para ustedes. Okay, so maybe there isn't for the moment any other question, but we will communicate you, Professor Siva, if there's any other question or follow-up question. And I'm sure that there will be persons here that will contact you to make further collaborations.
Yeah, definitely. That's what I mentioned. Like if anybody has a doubt or anything, please feel free to contact me, okay?
So I thank you very much, Professor Siva. We close today with the CC Tech. Be sure to connect tomorrow. We have other activities, other key conferences and thematic forums. Please be sure to access them because they will be very interesting. Thank you, Professor Siva, again, and we'll be contacting you soon. Thank you very much.
Thank you so much. Please take care. Please take care. Okay, every one of you. Okay. Bye.
Bye. Muchas gracias a todos. Por favor, antes de salir, asegúrense de registrar su asistencia en las ligas mencionadas y si tienen interés de registrar actividades 8 en 1, también está la liga. Muchas gracias a todos y nos vemos mañana.
Gracias.
Gracias, hasta mañana.
Hasta mañana.